Hello, and welcome back to the Cedille cast, a series of videos showing how to write programs and proofs in Cedille. This episode is the second and final part of a sequence showing how it is possible to derive induction for impredicative lambda encodings in Cedille. The first video showed a failed attempt at trying to do so using just the impredicative calculus of constructions plus dependent pair types. The point of this was to show where we get stuck in this attempt in order to motivate the new typing constructs that Cedille adds to the calculus of constructions in order to complete the proof. And along the way, we noticed our first crucial observation, that the proofs that particular numbers, or rather particular encodings of numbers, satisfied induction looked a lot like the encodings of the numbers themselves. So this first insight into completing the proof of induction is making use of this strange coincidence. Can we somehow take advantage of the fact that numbers are intrinsically inductive? Can we view them as being both their own iterators and their own proofs of induction? The answer is yes, we can, by introducing dependent intersections. Well, before talking about dependent intersections, which are somewhat of a rather exotic typing construct, let's just talk about regular non-independent intersections. Namely, the idea that a single term could have two different types. We can make this a bit more concrete with a simple example. The fact that in Cedille, 0 and true represent one term that has two different types, nat and bool. So let's first define bool. As is usual, a bool is defined as a type that takes two arguments and returns one of these. So inherently, a bool is a choice between two different things. True the definition of true is big lambda x, and then give me a then case. If we're thinking about booleans as sort of inherently being their own if then else's, then true takes a then case and an else case and returns the then case. And false, also bool, takes the then and else case and returns the else case. So ordinarily, languages with primitive inductive data types don't allow us to equate two terms of two different types. Of course, you can with heterogeneous equality, but you usually don't go even a step further and say in the type system that this term has two different types. But in Cedille, we can do this with the dependent intersection. So I can find a type bool intersected with nat, and that is simply unit x bool nat. And this is the notation for the dependency. X can possibly occur free and nat, but here it does not. So we'll put an underscore representing an unnamed variable, which just gives us a plain intersection. So again, in Cedille, bool and nat are just types that are inhabited by lambda abstractions. And if we look closely, we see that true takes two arguments and returns the first one. And this is exactly what 0 does. It takes two arguments and returns the first one. So even though there's a little bit of a strangeness going on, right? Because step is ostensibly ascribed with the type x to x here in 0, and else ascribed with the type x in true. This difference doesn't really matter because the step case in 0 and the else case and true are never used. And furthermore, when you erase the types and just look at the untyped lambda terms, they're exactly the same lambda term. And we can witness this. Sorry, I should go this way around. Now, the way to introduce a dependent intersection in Cedille is by this bracket syntax, square brackets, where the thing that goes in the left, bracket syntax taking two components, the left-hand side and the right-hand side. The thing that goes in the left-hand side is the thing on the left of the intersection. Here, that would be true. And the thing that goes on the right-hand side is a term of whose type is that found on the right-hand side of the intersection. Here, 0. So not only must we have that these two components are well typed with respect to the intersection, but furthermore that their erasures are the same. And again, if I say Control I in and look at the erasure of true, I get lambda then, lambda else then. If I say Control I in to look at the erasure and normalization of 0, I get lambda base, lambda step, base. And after alpha conversion, these are exactly the same term. And now you might ask, well, what is the normalization? What is the erasure of a dependent intersection? And the answer to this is, well, it doesn't really matter which side we pick, the left-hand side or the right-hand side, because they're both the same term. So Cedille arbitrarily chooses the left-hand side, and we see that the erasure of true 0 is the same as the erasure of true. So this is, so one more thing before moving on to dependent intersections. What can you do with a dependent intersection? This is the constructor form, how you introduce them. You also have eliminator forms. So if I say true 2, test type bool, and it's equal to true 0.1. This is saying I want to take this term true 0 and view it as the type given in the left-hand side of the intersection. Zero 2 of type nat, I can define by saying true 0.2. I want to view my term true 0 under the lens of it having type nat. So that's intersections in the non-dependent case. We will see the dependent case as we continue to try to prove induction for natural numbers. But the first thing we will do is rename this type nat. The reason being that this is not actually the type ultimately that we will be proving induction for. Instead, this is simply the same nat that you can define in the calculus of constructions without any of the additional typing constructs. So we'll call this CNAT for the constructions nat. As before in the previous video, we'll define a predicate over CNATs called INAT. Which says for a particular CNAT, the following holds. For all p, if p of C0 holds, and if pi m, p of m holds, then p of C successor holds, C successor of m holds, then p of n holds. Again, this is not exactly induction. This is just the property that a particular natural number is inductive. If I can show that p holds for z0, and that given, assuming that P holds for M, that P holds for successor of M, then P holds for this particular M. And again, in the previous video, we can define an I0, which is the proof that C0 is inductive by saying lambda P, introducing my assumed property, the assumed base case, the assumed step case, and then just providing the base case because it has exactly the type we want. Now, instead of defining I_NAT1, I_NAT2, etc., I'm going to define I successor, which says that for all M, CNAT, if P holds for M, if M is an inductive CNAT, then so is the successor of M. Now I need to introduce the proof that the successor of M is inductive, so I'll say give me a P, give me a base, give me a step, and what I'll do here is say that I need to, I'll use my step case. So let me bring up the inspect buffer with I and the context with C, and say I need to prove P holds for the successor of M. My step case will give me P holds for the successor of some M, bound over here, provided that I say the M that I want to give and a proof that P holds for M. So I'll say step apply to something and something else. Here, the CNAT that I want to prove this property over is M, because I'm going to show that P of M holds in order to allow a step to then show that P of successor M holds. And in order to show P of M holds, I'll use IM. Sorry, let me bring that back. IM, which is a proof that M is inductive, and invoke IM on base and step. Now, we have our CNAT, the natural numbers from the calculus of constructions, and INAT, the proof that these CNATs are inductive. Let us define NAT. NAT is the intersection of those CNATs which are also proofs of their own inductivity. Oops. So again, this is a very strange type. How can a term be typable both at some simple type and as a proof of a property of that very term at that simple type? We can, again, give some intuition for this by defining the first natural number, 0, has type NAT, and it is equal to, again, we're trying to form a dependent intersection. So we open with square brackets and place two holes for the left-hand side and right-hand side. For the left-hand side, we must inhabit the left-hand side of the intersection, CNAT. We have such a term, C0. For the right-hand side, we must give a proof that C0 is inductive, which we have with I0. And then just like with our non-dependent case, we must have that the erasures of C0 and I0 are the same term. So if I say CIN, normalize, CIN, normalize, I get two untyped lambda terms which are the same. And of course, the normalization of 0 itself is lambda base, lambda step base. So there is this sort of strange self-reference going on, right? This I0 is, in a sense, a proof that it itself is inductive, because the lambda term for the lambda erased lambda term for I0 is the same as the erased lambda term for C0. So this sort of weird self-reference in the type of I0, and that it mentions an alias for itself. But this self-reference is contained by the fact that it can only be done through the simpler view, the simpler view given for the left-hand side of the intersection. We can also define suck, or rather, we won't be able to if you were paying careful attention. You'll notice that there's actually a bit of an alignment issue with our definition of inductive successor and the constructions successor. Namely that the inductive successor takes 2 arguments and the constructive successor takes only 1. So let's see how, let's see what Cedille tells us when we try to inhabit this type as it is now. Give me my in, and now I'm going to inhabit a dependent intersection. The left-hand side, I want to say, is C successor of n.1. Again, because C successor requires a CNAT, but n is a NAT, so I'll just project out the view of it as a CNAT and feed this to C successor, and I'm fine. And of course, the erasure for this is step applied to n iterated over n fed its base and step. For the INAT case, we run into trouble. In order for I successor in order to satisfy the requirements of I successor, in order to produce an INAT of C successor, I have to give it n.1 and n.2. But now Cedille gives us the underline and bold of a grave mistake, and that mistake here is given as in this error. The 2 components of the iota pair are not convertible. Here, the head normal form of the first component is step just applied to n base step, but in the second component, I have this additional argument n, and actually, this may be a little bit confusing if you're just looking at this, because you might expect this to be step n.1 applied to n.2 base step, and similarly here to see a projection is basically making this whole type. But Cedille is giving us the erased versions of these terms, and the thing to note about that is that projections, I erased them. Projections are also erased, so the erasure of n.1 and n.2, both of those are just n. But regardless, even as erased terms, these 2 terms are not convertible because step is given 2 extra arguments. Well, what can we do about this? We can't just drop the first argument, because if we did that, we would have no binder for m. This would not be a well-typed expression. But this is pretty frustrating, right? Because we don't actually care about this m so much. We only need it so that we can describe which CNAT this proof is over. But the thing we only care about, the thing we really only care about, is the proof itself. In a sense, this m is irrelevant, and what we need is a relevant quantification. And actually, turns out, we've been using irrelevant quantification this entire time. It's for all. In the previous video, I said that you could just think of for all as being quantification over types, and that is true because types are always irrelevant in Cedille, but we can also quantify over irrelevant terms. These are terms that we only need for typing some expression, but that otherwise don't show up in the runtime, as it were, of the term. It plays no computational value, only a way of annotating a definition so that we know that we can check that it is well typed. So here we'll make this change, that m is irrelevant, and here that I successor takes an irrelevant first argument. We, just like with quantification, just like how with types and irrelevant terms, we quantify over for all. With types and irrelevant terms, we abstract over them with a capital lambda. And for applications, if I type this currently, I will get an error saying that the irrelevant variable m occurs free in the erasure of a body. That is to say that it's given relevantly in a computationally relevant position. But step takes as an argument an irrelevant term. So in Cedille, you must also mark application of a function to an irrelevant argument with the dash, so that it knows that this would be, it's easy for it to conclude that this would be safe to erase. And finally, we come back down here and say the second argument that was causing us so much trouble, the second argument that was causing us so much trouble is actually totally irrelevant. Now, if we look at the erasure of this, we say, hey, it's disappeared. It was only there in order to allow us to type the second argument, and when we erase the terms, we erase everything that's irrelevant, including types and irrelevant terms. And this gives us what we need. The normalization of this intersection is lambda base step applied to n base step, which is exactly the erasure of the left-hand side and the right-hand side of the intersection. Again, noticing that there's this sort of weird self-reference going on, that we know that C successor in point 1 has the same normal form as I successor applied to an erased in point 1 applied to a relevant in point 2. So we're in the type of this expression, we're sort of referring, the type of this expression is sort of referring to itself, but only through the view of this left-hand side, which is a weaker version. So now that we have our nat defined as a dependent intersection and our constructors for nat, 0, and successor, we can make some progress defining induction. Unfortunately, this is not all we need. We have 2 of the 3 components that are required, but to motivate the third component, let's try to take a stab at proving induction. I should also mention, in case you're wondering, if it looks already like we have induction, right? I mean, nat intrinsically says that this version of itself, CNAT, has an induction principle. So we do have induction for CNATs, but this is not quite the end game. What we want is a type, nat, for which we can prove induction for nat. And not only will we fail once, we will fail twice. Spoiler alert. There are two small steps to proving induction. But anyway, let's say induction nat fail is the type for all p, nat star. Give me that p holds for 0, and that if p holds for m, p holds for successor m, then give me any n, and I'll return a proof that p holds for n. P, add a base, add a step, add a n. So again, if we're thinking that we already have everything we need, we know that in our context right now, we have n, which gives us a form of induction on CNATs. So we could say, all right, give me my n, and project out the view of it that allows me to reason by induction, provide p as the motive, and then just apply it to its base and step case. Well, unfortunately, this is not going to work. And the reason is that the p that we've described is a property over natural numbers, but as a property over nat, but the p that we're allowed to use from in point 2 has to be a property over cnats. So there's this mismatch. What we need is some way to convert properties over nats, properties over cnats to properties over nats. And what we in effect need is a way to convert this cnat to a nat in order that p can properly apply to it. So we'll comment this out for now. And we'll write a conversion function. cnat to nat, which says, give me a cnat, and I'll produce a nat. What does this term look like? Well, perhaps not surprisingly, we can compute this simply directly from iteration. If I take my cnat in and I apply it to the base and step case, my base and step case, of course, being 0 and successor, then I'm able to produce a natural number. cnat instantiated to nat with 0 and given successor as the nat to nat function gives us a nat. And furthermore, we should know intuitively that if I iterate n times successor applied to 0, I should just get n. So will this be enough? Well, as you might have guessed, no, because I'm naming this function fail2. But we get closer. Here, instead of, oh, that was silly. Sorry. Properly, this should have been p of x. Now, no wonder. Now the error here is that I've given a cnat, but I expected a nat. Here, I'm expecting cnats, but I've been provided with nats. Of course, this is ill-kinded. So what we'll say here is that we've been given a cnat that we've named x in our motive, and we're going to just convert it with cnat to nat x. Drat! What went wrong? So we've got a type error, but now it's an issue of conversion. I'm expecting, Cedille is saying that I'm expecting a proof that p holds for n, but what you've given me is a proof that p holds for this converted n. And again, this would be this would actually more well typed. This would be cnat to nat in point 1. And we know, again, as we said before, we should have by a reflection law that cnat to nat in is just n. By applying n to 0 and successor, we have effectively just rebuilt the natural number, but now with this fancier nat type instead of the cnat type. So what we need, finally, in order to prove induction, is a reflection law. For all m type nat, n is equal to cnat to nat of n point 1. And now we introduce Cedille's third and final new construct added to the calculus of constructions, which is a built-in equality type. But this is not your everyday equality type. It is not homogeneous, and as we'll see, in fact, it's not even it's not homogeneous, as we'll see. In fact, it's not even heterogeneous. Cedille has an untyped equality. So the equality that we state is between any two untyped, can be between any two untyped terms. And in particular, I do not need to provide the projection here in point 1, but I will do so for the aid of readability. What I'm saying here, in effect, intuitively, is that the natural number n is equivalent to CNAT 2NAT applied to the CNAT that you get from n, and then CNAT 2NAT will just rebuild it. But I could actually have just said CNAT. And now I have equality between two things that should not be the same type, where n should be a CNAT, and CNAT 2NAT n should be a NAT. Well, how do we make use of this? Ordinarily, as we saw in the last video, you would try to prove a reflection law using some kind of induction. Induction for which we do not currently have for the full NAT type. But we do have this limited form of induction for CNATs. And it turns out this is all we're going to need. I will say, invoke my induction principle for CNATs on the following motive. For any x CNAT, I have the case that x is equal to CNAT 2NAT x. Again, even though the type signature that I've given here, could be well typed, the type signature given in the motive is at the very least heterogeneous, because x is a CNAT, and CNAT 2NAT x is certainly a natural number. But it turns out that as far as equality is concerned, we don't care about the ascribed types. In Cedille, equality is only beta eta equality and alpha convertibility. Specifically, beta eta alpha equality of untyped lambda terms. Here, I need to give a proof that C0 is equal to CNAT 2NAT C0, which by just doing a simple substitution, by saying C0 applied to 0 and step, we'll ignore the step and just return 0. And of course we know that 0 is equal to C0. So I can just say beta, which is in Cedille, the former indicating that a equality that you're trying to prove is true by simple beta reduction. You can also think of beta as REFL. Let's give an example of this, actually. Just example of beta has type xx is equal to lambda xx, and it's so beta is REFL, and it's the inhabitant of obviously true equalities. And even though it may not seem, because there's quite a bit of conversion going on, it may not seem that C0 is equal to CNAT 2NAT C0. It is true. I'll leave it as an exercise to the viewer to work this out either by hand or in Cedille. But these two terms do, in fact, normalize to the same term. Normalize to the same untyped term. to prove the step case, we can assume an m, an irrelevant m, and assume our previous case, that m is equal to c nat 2 nat m. And now we must prove that c successor of m is equal to c nat 2 nat m, c nat 2 nat of successor of m. The successor of m is equal to the successor of m after having been converted to another natural number. So beta was our introduction form for equality, and the elimination form is notated by rho. So rho performs a rewrite. Given an expected type of an equation, given an expected type for an expression, give me an equation to rewrite by, and I'll rewrite all occurrences of the left-hand side with occurrences of the right-hand side. Here, I want to be a little bit more aggressive because I don't want to just actually, yeah. I want to be a little bit more aggressive because I don't want to rewrite simply left to right in this way, because if I do, I'll get c successor of c nat 2 nat m is equal to c nat 2 nat m of c successor of c nat 2 nat m, which doesn't get me anywhere. What I want to do is to be able to normalize these two expressions, because both of these are actually redexes. Normalize and then perform rewriting. So to that end, Cedille provides an augmented form of rho called rho plus that performs beta reduction while it's looking for matches to rewrite the equation by. So I'll say rewrite by equality and then see what I get. And again, you can see Cedille has been a little bit more aggressive in unfolding the definitions. But what I see on both sides is abstraction over a base and step case, and then step applied to c nat 2 nat m base step, c nat 2 nat m 0 successor base step. Ah, I see. So anyone who's used interactive proof assistant before and had to deal with equality will know the situation that I'm in right now. This does not actually look obviously equal. And in fact, if I ask Cedille about it, it will say that no, I'm not convinced that that these two terms are actually beta equal. And the whole reason is that I've rewritten in the wrong direction. So I have another nice little combinator sigma, which is symmetry of equality, or operator sigma, and that says that given that eq is a proof that m is equal to c nat 2 nat m, sigma eq is a proof that c nat 2 nat m is equal to m. And if I rewrite by this, going in the other direction where I'm collapsing c nat 2 nat m to m, I only rewrite I'm only rewriting the right-hand side of this equation that I'm trying to prove, which makes it which sort of collapses it and then allows me to then prove that it gives me two expressions which are in fact which normalize to each other. I mean, this right now is successor m applied to two abstractions, but if I normalize successor m just a little bit, I'd get this lambda term. So coming out of the weeds a little bit, just to recap what we've done, we have now proved a reflection law for natural numbers. That if I take a natural number and I project out the simpler version using n plane 1, and then I rebuild the CNAT with my NAT constructors, 0 and successor, that ultimately what I get is the same natural number that I started with. And now I'll be able to prove this property. So first what we'll do is take this expression and give it a local name. I will say proof is equal to, so in Cedille, this bracket notation without comment, bracket notation with a term definition in it and without a comma represents a simple let binding, and then the rest of the let is given after the dash. You'll see here in a little bit once I get Cedille to stop giving me this angry highlighting of error. I can say what is PF? Well, it's the type that we had before, that P holds for our converted M. I'm not happy about. Right. Again, yes, step is defined in terms of nat. This conversion is much easier. Step is defined in terms of nats, but the type that we need to give for this, the step case that we need to give is something that's defined over CNATs. But it's easier to go. It's much easier to go from nat to CNAT. Lambda m, lambda proof prime, I'm going to say step applied to step applied to m of PF prime. Sorry, I'm missing a parenthesis here. Right. So this is still not quite right. I gave it a CNAT, but I gave step a CNAT, but of course step requires a nat, so I'll just say CNAT 2nat m. Sorry if that was a little bit difficult to follow. I'll just recap. I noticed that I also had to revise the definition of step in order to make it type check. I need to give a term that shows that for all m, if P of the converted m holds, then P of the converted successor of m holds, or we're converting from CNATs to NATs. So I introduce my m and my proof, and now I must show that P of my converted successor of m holds. And what I've given, of course, is that P of successor of the converted m holds. Note this, you can see that the successor is that by a single step well, you can see that the successor has sort of bubbled outside of the call to CNAT 2NAT, indicating one step reduction of CNAT 2NAT. So this, of course, is fine. These two types are convertible. But in order to prove that P holds for successor of CNAT 2NAT M, I invoke step. I must give it a natural number. That natural number is the converted M. Now I must provide a proof that P holds for the converted natural number. But of course, I have this in the context already, PF prime. So now, even though I have a proof of P of the converted N, I must make the final step using my refraction law to show a proof that P holds for N. And with that, again, I will simply perform a rewrite of ref nat of N and supply proof. And that concludes the proof. We've shown with taking the calculus of constructions and adding 3 new typing constructs, dependent intersection, quantification over relevant terms, and untyped equality, how we can prove induction for lambda encoded natural numbers. Hope you enjoyed this video. Thanks for watching, and see you in the next one.